and I think we can get started. Okay, so welcome everybody. Good morning to everyone joining us in North America, and good evening to those of you joining us from Europe. I just have a little bit of background noise. If everyone could remember to just make sure that they're muted, that'd be excellent. Thank you. Okay, it's great to have so many accomplished foundation professionals with us. My name is David Zanchetta, and I've been working for Berminghammer for about 8 years now. We also have Dennis Shoemaker, a professional engineer on the line, and he's one of our most experienced design engineers and an expert in lead. Yeah, sorry, Dennis. And an expert.
Good morning, everyone.
He's an expert in lead stability analysis. Milan, my colleague, is on the line. He is helping moderate today. You can say hi, Milan. All right, so what Milan's helping with is if you do have a question, you can use the conversation window in Teams and ask the question there, and Milan will group the questions at the end of the presentation. I will take those questions. So we might as well get started. So today we're here to talk about vertical travel leads, our new line of H-series leads, the history of why VTL exists, and how they help foundation contractors. So the agenda, first we'll talk about the history and how they were developed, which leads really well into features, because one of the reasons they were developed were to achieve certain features. After that, we'll look at different applications. Many people think of vertical travel leads and they associate them almost primarily with pile driving. That couldn't be further from the case. There's lots of other applications that people are using vertical travel leads for. We'll take a stab at the spud lead versus box lead debate. I know people kind of argue the merits of both and trying to determine which one's the best lead. I'll try to give my opinion on that and try to give you a clear winner. Then we'll move on to the new series of leads, the H leads, the H25, H28, and H36. So those are our new spud leads. Following that, what we'll do is we'll go through kind of a case study stability analysis example. That's what Dennis is going to help us with. We're going to start from a pile that needs to be put into the ground and determine from there what size lead, what tool, what crane makes sense, what crane might make more sense, and then come to a conclusion there. So we're going to do all of that live. Then we're going to do a little bit of a question and answer. Like I said, if you do have questions, you can just put them into the conversation window, and Milan on the line will group them to ask them at the end. Actually, before I move on from that previous slide, I just want you to remember a couple things. I'm going to open up my laser pointer here. One of the key features for VTL are these slides. So right here, this lower slide, that top slide, and the vertical travel winch. Now that winch can be on the lead, it can be in the crane. I just wanted to highlight those couple of things before we move on. Okay, so the history of development. We start with the history of vertical travel leads because it helps understand their features and how they are applied. So it was in the 1960s, Bill Bermingham developed and patented the vertical travel lead. You can see actually in this picture, both box leads, so the far left, and spud leads in the same photo. So the development was kind of going on around the same time with both sets of leads. This picture is actually taken from the Pickering power plant, which is the power plant that powers the city of Toronto and surrounding areas. So why were they developed? Hanging leads were a little bit too slow to position. So hanging leads are excellent. You can go really long with them, so meaning you can drive really long piles. You don't have to do as much splicing. They're really good from that perspective, but they're a little slow in terms of positioning them. So the traditional way of positioning them is to have a couple guys on the ground physically moving the leads into position. So when you have tolerances of like an inch or 2 inches, it's a little bit harder for the guys to get it into those positions easily. And then it becomes even more complicated if you have to put the lead on a batter because you need to drive a battered pile. So you get it into the perfect position and then you start lowering the lead sinks a little bit, you're off position. So there's reasons why they wanted to kind of help with that final positioning and by having a spotter that could help. So that was kind of the direction that they started going in. In this picture on the left, you can kind of see one of the first primitive spotters. Now this wasn't hydraulic. I'm pretty sure it's just steel going out to the back side of the lead there, and they were just trying to help to position the lead so that when they leaned back with their boom and got that batter, it would stay in position. So that's kind of a very primitive spotter. They used to actually be called kickers. They kind of moved towards spotters afterwards, the name spotters afterwards. So you think, okay, well, why not use just a dedicated rig, right? Why not just get a rig that does pile driving, not a crane, don't put a set of leads on it? And the short answer is we tried that. We had dedicated rigs, tried a couple of them. And one of the things that we found didn't really work very well for us and for Bermingham as a company was that we needed to reach further out than what we could do with a dedicated rig. We did a lot of work over water. So dedicated rigs you could work in right beside yourself, and they're great for open field construction. You can put in a lot of piles where if you don't have any limits, but when you have to reach out into the water or drive a pile out into the water, it becomes a lot harder because you have to be right beside it. So we continued on with crane mounted leads, and we added a slide and a boom tip connector. So we have a spotter, slide, and boom tip connector. And with those, we were able to achieve those batters a lot easier. So this is a photo of a 3-to-1 batter taken in 1968. You can see that this is actually the same year as the Pickering plant, so a lot of development happened in that year. You can see that the spotter is now hydraulic. You can see that the boom tip connector, let me bring my laser pointer up at the top here, has a slide on it. And you can see that there's a line for the vertical travel. In this case, the line came down the back of lead to the crane. So because of the ability for the lead to go up and down, we can now still position this lead really close to the ground to get our location accurately. And we could get into this batter relatively easily instead of having a set of hanging leads where we have to kind of have a really long boom, tilt back into ourselves and hope that our position doesn't move much on the ground. We can, if we're off a little bit on the ground, we just move our spotter out and vertical travel down. So the need for vertical travel came from limitations of what else was available on the market. So one of Berminghammer's first customers for VTL was the rail industry, and you can see why. The railways wanted to be able to drive piles for new bridges from their tracks. They needed working range so that they could drive the piles for each bent out in front of them and needed to be able to drive piles at a batter. So you can imagine this crane comes in, it's the only thing on the track, nothing exists out in front of it, and it needs to put in a new bent for a bridge. It needs to be able to reach out so that it can drive piles. So you can see actually the couple of vertical piles in the middle, and then you can see on a slight side batter, this pile on these piles on the exterior. And still to this day, the railroads are one of our larger customers. This particular photograph was taken of a system that was delivered to them this year. So now that we know a little bit about the history of vertical travel leads and why they were developed, we'll talk a little bit about the features. Now, the first feature of vertical travel is obviously a vertical travel. The photo on the left, you can see that the lead has been lowered into the excavation. This allows you to, again, be able to align your pile, align your lead so that you're very accurate at the bottom of the excavation while your crane still sits up on top. Again, we're sliding at this slide. In this case, this is our vertical travel winch. So we pay out line and the lead lowers into that position. A more extreme example is on the right. You can see that we're driving into a very deep existing excavation. Every hole in this lead is a foot, so we're at least 20 feet down the excavation at this point. And you can see there's actually a little bit more room up at the top of this boom tip to slide the lead a little further down. So some pretty interesting applications. There's also the application of going up too. So if you imagine if this wasn't an excavation, if we had to go up a hill here, you lift this lead up and now you can go up that hill fairly easily. So it's very maneuverable, really helps with positioning piles. And it's just quicker than a hanging lead. So again, to illustrate this, this function, I'm just going to show a quick video. You can see that the lead just goes up and down, and it's really obvious without anything else in the background here to see how this works. So another feature of vertical travel leads is extreme batters. Now the picture that you're looking at, it was taken in at the container terminal in Kingston, Jamaica. there was a 3-to-1 batter shown in this photo, and it was 120 feet, so 36.5 meters. They did both H and pipe piles on this project. That particular one in the picture is an H pile. And the lead itself was 147 feet, so 45 meters. I'm going to jump back and forth between metric and imperial just because we have both audiences on the line here. So now the extreme batters are accomplished by having your spotter extend. So in this case, we have a hydraulic spotter. The animation is going to show you a 2-stage spotter going out and then coming back in. And the actual picture, again, in the container terminal there in Kingston, Jamaica, has a 3-stage spotter. So if you imagine, instead of just 2 boxes on the spotter, we have 3. So a box and a box and a box. Now, just to show you a couple more examples, again, that was pile driving, but these extreme batters can also be done. We've got a vibro mounted on the lead. I saw some vibro manufacturers on the line, so we do put these on the lead when we have to achieve these certain batters. In this case, it was a container terminal in Boston. And then in the center picture, we're doing some drilling on a 2-to-1 batter, so it's very extreme in the city of Toronto. And then in New Jersey, I believe, on a barge with a 300-ton crane doing some in batters. I might be wrong with this, but I think it was either a 20 or 30-inch size pile. So another great feature of vertical travel leads are their reach. So if you remember that little dedicated rig, really hard to do what you see on screen right now with that. So we have, in this case, on the left of the screen, we have a configurator drawing that would have been done by someone like Dennis on the line before the project to see exactly what the working range could be. In this case, with the crane shown, we could go between 51 and 70 feet. So that's 15.5 to 21 meters out from the center pin of the crane, making the picture on the right, the actual picture, a reality. In this case, they're using a vibro to install the pile. And I can show you a little bit about how that works in the animation. So as the spotter moves out and you boom down, you move your reach out. Meaning anywhere within that reach, so anywhere within that sequence, you can put in a pile, drill, or whatever your application is. So from one setup location, you can hit multiple spots. Okay, some people often ask us, okay, how do you isolate the torque from the boom of the crane? So we have 2 swivels on our lead systems when we need to do drilling or anything that involves any torque. The swivel is shown here in this animation in blue, and if you just watch the first little part of the animation, it'll swivel left and right. And then the animation goes on to show the other ways that we swivel. But that degree of freedom basically decouples the lead from the boom and allows it to be basically free up at the top there. So you won't transfer any torque in through the boom. Now, where do we transfer the torque? So that's the lower swivel, and you're taking a look at an animation of one there. So remember, attached to the kicker or the spotter, we have this torque resistant swivel. So we're holding it stiff at the spotter so that it can't twist. And you also have the added benefit when it's hydraulic like this to be able to twist side to side if you want to position yourself. So you'll see how that works right here. All right, now that we know some of the features of vertical travel leads, we're going to talk a little bit about the applications. You can see some of them up in the slide right here. One-pass drilling. So one-pass drilling, the loading sequence involved with it involves raising the drill string and down the hole hammer up, over, and into the pile before lowering it down to lock into the ring bit that's installed on the pile. So essentially, to do that operation, you need double the length of the pile in height plus a little bit for your drill. So vertical travel leads lend themselves really well to this because they can be really long. And additionally, this type of drilling is traditionally done, or most applications are used over water. So having a good working range, so having a spotter from a vertical travel lead gives you a great working range as well. So I'm going to show you a little quick video here of some one-pass drilling. It's a time-lapse video, so you won't really see the loading of the pile because it happens so quickly. I'll try to point it out as we go. Okay, so they're installing the pile here, one pass, and then they come out. Now they go grab another one, see how fast they grab that, and they're drilling the next one. Same thing, go grab a pile, drill it, go grab a pile, drill it. I'm gonna play that just one more time so you can have a good look. As you can probably tell by the French on the top, this was a project in La Rochelle, France. So another application for vertical travel leads is extreme depth CFA in one pass. So we had a customer come to us, and this has since been repeated a couple times, needing a depth of 156 feet, so 47.5 meters of 48-inch, 1.2 meters diameter CFA to be done in a single pass. Now you can accomplish those depths using other rigs, but they would involve adding in sections of auger. So the one pass was key to productivity for this customer, and we developed a rig using our H36, developed an vertical travel lead so that they could accomplish this. So a similar theme with soil mixing. There's lots of soil mixing rigs on the market. However, if you need to go deeper than what's available on those rigs, a lead system with vertical travel helps a lot. You can again have a spotter with some working range, and basically you're making yourself a soil mixing rig that can go deeper than your other ones, anything commercially available. Now, another great application is pile driving. So in this case, we have a 60-inch, so 1.5 meter diameter pile, and it's almost 44 meters long, 144 feet driven, and it was driven without a splice. So these piles actually came in by boat, never had a need to splice them. It was actually estimated that if the piles were spliced instead of being driven on this project in one go, that each splice would have taken 3 days to complete. Now, this project had about 2,000 piles on it, so you can see how much time savings was saved by having piles come in full length instead of having to splice them. Another application is extreme length H-pile driving. This particular photo here, we see that they're lofting a 135 foot, so 41 meter long, 14 by 117 pile in one piece. In this case, they actually did the splicing. The piles came in shorter sections, but they spliced it on the ground. So by splicing it on the ground, they kind of took the splicing off of the critical path, meaning they could just have workers continuously working on splicing the piles while the lead system and hammer never stopped working. Another application is extreme depth CMC drilling. So we had a customer come to us very recently, actually needing to go 170 feet, so almost 52 meters in penetration depth with their CMC. There aren't rigs available on the market to be able to do that, so vertical travel makes sense. We could find a lead section that made sense to do this, and you can see the customer drilling with a couple of them right here. Wick drains, again, a similar vein. There's a lot of dedicated wick drain rigs that are out on the market, but in this particular case, the customer needed to go to a depth of 150 feet, so 45, almost 46 meters. And we took a lead, an existing lead, and added some tooling and used a vibro actually to penetrate the mandrel, and came up with a lead that could accomplish the 46 meters depth. So lots of different applications. Pile driving is kind of just the tip of the iceberg. Now I'm going to take a second to talk a little bit about the debate, box leads or spud leads, which is better, VTL. So the left picture there, you see a very large system. Take a look at the bottom of the picture, you can see the people to give you an idea of the scale. And this actually a slightly similar length, slightly shorter on the right side of the H36 system. So the H36 is the spud, and the box leads are on the left. Just to give you, again, an idea, most spud leads on the market will look like this, and then box leads have your deeper sections and have a spacing in between for the tool to ride in between. Spud leads have the tool ride out on the front. So I'm going to talk about the pros for each, because the pros of each of them are really the cons, so it's kind of be a little bit redundant to talk about the pros and cons of each. So box leads, they're pros. They're typically less weight per foot than their spud equivalent. So less weight is always good when you're lifting things. They have a deep section and can loft easier. So you can have really long leads. So leads don't start up vertical, right? So you have to lift them into position. And when they're horizontal on the ground, they act much like a bridge, right? You have the deeper the girder for the bridge, the longer you can span. So if you have a deep box lead section, you can span a big distance, which is why for really tall applications of pile driving, box leads are awesome. Also, many hammers are designed to run in them. So because there's been so many hanging leads over the course of history, a lot of the hydraulic hammers, diesel hammers have all been designed to go in those hanging leads. So very easy to swap them out. So now some pros of the spud leads. Biggest pro is probably that there's a much higher torque than box leads. So because you've got this opening here on a box lead, you lose a lot of your torque properties. Think like 4 to 5 times more torque in a spud lead than a box lead. So it also allows for many tools. You can run obviously your hammers, hydraulic, diesel, vibros, drills. You saw the other tools we were running in the other applications, and they're all run out in the front. So we've run into a lot of times with box leads where if you want to put a tool in it, but it doesn't fit between the cords or it doesn't fit for the depth. So that's why spud leads has got an advantage in terms of universality of being able to use it for lots of different applications. Another advantage of spud leads is that they can handle tighter pile arrangements, meaning if you have a pile, so follow my laser pointer here, so it's a pipe pile, and then you have another one right beside it in your layout, this cord here is going to interfere with that. When you're using a spud lead, because you're working out in front, you won't have that interference. Another minor point is that spud leads typically ship in less loads just because they're smaller. You can fit a bunch of these along the bed of a truck versus these. You kind of have to stack them, and then height becomes an issue too. So I know I sound like I'm hedging here, but I'm going to give you kind of my own personal opinion and overall conclusion. I find that the overall better lead, if you're doing both piling and drilling or any other applications, is going to be the spud lead. That being said, the box lead really excels for really long pile driving applications. So if that's your bread and butter, if you're a pile driver and that you're not going to really ever do anything else, you can get a slight advantage on the total length of your system by using a box lead. So the next thing for our presentation, we're going to focus a little bit on the H series of leads. So these are a little bit newer for us. We've been developing over the past, I'd say 4 or 5 years. They are, if you're familiar with our older series, they were slowly replacing the L series of leads. So your L15s, your L18s, L23s, L27s, and L27 HTs. The reason that they're replacing them is because we wanted to go to a little bit more torque. We want to get a little bit more torque out of our spud leads. A great comparison actually is to follow these two leads, so the L23 and the new H25. So the L23, they're very similar to each other. 230 pounds a foot, and the H25 is actually a little bit lighter, 5 pounds a foot lighter, which is great. The other dimensions in terms of their width and their depth are all very similar. But if you take a good look here at the torque capacity, your L23 can take about 65,000 foot-pounds, and your H25 can take about 200,000 foot-pounds. So easily 3 times the amount. And they're a little bit lighter. So we're moving from the L series to the H series for that reason, because we can do so much more in terms of torque. I'm going to talk a little bit about each of the leads next. So the H25, so that one we just talked about in replacement for the L23, it can go up to a height of about 138 feet, so 42 meters. It is capable of withstanding about 210,000 foot-pounds of torque. And it's kind of designed at going around 120 to 250 ton cranes. And you might be thinking to yourself, like 120 to 250 ton cranes, that's a crazy range. And it really depends on what you're putting on front of it. So in this case, we're doing some CFA with the Bauer MC96. And because we're working in very close to ourselves, we can accomplish this. But if we put anything heavier there, we're going to have to go to a larger crane. So now we're moving to the H28. You can go up to 186 feet, so 57 meters tall, 250,000 foot-pounds of torque. So you're getting up there, and you're going anywhere between 175 to 250 ton cranes. This photo that you see here is again a CFA application in Hawaii. This crane was an MC128 from Bauer. The H36, so the largest spud lead that we currently manufacture, can go up to a height of 205 feet. There's some debate as if it can go a little higher than that to 215. Right now we'll stick with 205 and say that it can go to 62.5 meters. The torque it can take is a 350,000 foot-pounds, and it goes anywhere between a 250 and a 350 ton crane. Again, it depends on what exactly we're doing out in front of it. You can see both examples there. It's the same lead. One of them is doing CFA work, and the other one's doing really large diameter pile driving. To give you an idea, kind of in one slide here, we can move from left to right, and you can see that the H25, again, it's got a great crane range. I mean, you can go from anything 120 to 250 feet, and you're maxing out at 138 feet. So there's lots you can do with the H25. If you want more torque and a little bit more height and want to go to the H28, you're looking at a crane somewhere between 175 feet to 300. Sorry, a crane from 175 tons to 300 tons. Again, going a little bit higher, you get a little bit more height and more torque going with the H36, so 250 to 350 ton crane. Okay, now that we've gone through the new H series of leads, I want to do a little bit of a case study example. And this follows very similar to what we'll often do on our projects. Quite often a customer will come to us and say, I need to install this pile. What lead and what crane do I need? So in this case, it's a fictional example. The fictional example I made up is to case advanced reverse circulation drill 30-inch piles, 50 feet long in a 4.5 meter square grid. So as we go through this case study, we're going to determine what lead size makes sense, how large of a crane do I need at minimum, and then maybe how many piles can I drive from one location, right? We'll take a look at that 4.5 meter grid and say, okay, we can tackle 3 piles from one location. We can tackle 8 piles from one location. So here's the grid. If you can imagine your crane sitting where it says typical drilling project, we're going to try to install these 30-inch diameter, half-inch wall, 50-foot long piles at approximately a 15-foot by 15-foot, so 4.5 meter by 4.5 meter grid spacing. Now, the first thing we got to figure out is what lead we're going to put them on. Now, to do this, like I mentioned in the one pass drilling application slide, we need to be able to load the drill string down the hole hammer into the pile and then connect the ring bit. So the photo on the right shows that layout. So the 50-foot pile, I double it and I go to 100 feet of lead, and then I need a little bit of height for my drill here. Now you might say that drill's pretty close to the top, but remember I've got vertical travel, so if I need to go a little bit higher, I can vertical travel pull this lead up a little bit, so that I've got more clearance on the drill. So because in this situation, it makes sense to use a BRC 75, that's a drill that Berminghammer manufactures with 75,000 foot-pounds torque. It easily fits into the H25's torque capacity of 200,000, so no problem there. And it's 108 feet, so it's less than the 138 feet max that we can use for H25. So again, really no problem there. So now that we've got that figured out, I'm actually going to turn over the controls to Dennis. If you could take control, unmute yourself, and you can go through the configurator.
All right, welcome everybody. So I'm sharing my screen here.
Perfect.
Yeah, so this is some in-house developed software that does stability analysis for our lead systems, and like typically we call it our configurator. So it lets us input all your data into this program. We'll evaluate the stability of the crane, and we'll see what kind of if we can meet the requirements of your job here. So we'll go through the steps and evaluate David's problem here and see what kind of crane and what kind of reach we can get here. So beginning, you can see sort of right up here, we have a whole bunch of different tabs to enter all the data. So like David mentioned, we're looking at a drilling job. So we'll choose drill. We chose a BRC 75, which is our RC drill. We're going to be using a down the hole hammer. So next one thing is asking for is drill string weight and length. So David, were you thinking of our 20-inch drill string for this job?
Yeah, that sounds about right.
All right, so for this job with a 50-foot pile, I'm going to choose like 40 feet of drill string plus a crossover, which is a total length of about 44 feet. That weighs typically around 12,000 pounds. A down the hole hammer with a shock sub and a bit for a 30-inch pile. Generally, that's about 9 feet long and weighs just under 10,000 pounds. So I'll put 9,500 in there. So we got all the information for our drill tooling in. You can see it's pretty easy to change lengths and weights as we go through different manufacturers and enter the specific details for a certain job. So next we enter our pile information. So like David mentioned, we're a 30-inch, half-inch wall pile and 50 feet long. So next option here is we're choosing our lead. So you can see we have all of our different lead sections built into this tool, so we can easily switch between the two. So like David mentioned, we're going to choose H25. By default, it chose a 69-foot lead length, which would be fine if you had like a rat hole or could put your pile in the water to load. But since we're doing first pass or single pass drilling, we needed 108 feet of lead to be able to go up and over. So we'll enter that. Next, we get to choose our crane. So here you can see we've got all these different crane manufacturers already loaded in our database. So this is either based on previous projects or options we've investigated. So we'll start on the lower end. So David said 120 ton to 250 ton with the H25 lead. So we'll choose a Manitowoc 12,000, just generic counterweight. So just typically takes a load chart from the manufacturer. If we have specific load charts for specific counterweights, we can get all that data entered in. So I'll choose an 80-foot crane boom. And then one of the important part of these systems, like David mentioned, is the spotter. So again, we have all our different spotter models loaded in here. I'll start with a relatively short one just to see where we end up. Different pile gate options. So for a 30-inch pile, we want to choose a 31.5-inch opening just to give a bit of clearance on there. For component options, we're not going to use an upper VT block. So that gives you a bit of an option if you need to swing the lead back and forth. On quite a few systems, we end up reeving the VT line through the boom tip shivs. So then that component's not required. We'll stick with the VT winch, and with the H25 lead, sometimes we do not need the line deflector. So those are all just details that we can talk about later. So again, we've got sort of all the preliminary data entered in there. We'll hit the calculate button and see where we end up. So it's going through, putting all the mass of all the different components in there, comparing it against the load chart, and we get this result. So what we see here is it's able to pick it up, but really we've got 7 inches of working range. So right now the minimum working radius is governed by the boom. So the boom angle of the crane, we can't bring this boom any higher. And the maximum radius of the system is governed by stability. So here we're at 95% of chart. We typically leave that as the upper limit of stability just to give a little bit of margin for position and weight. So this isn't a system we'd recommend. So it's really to get any, you can see it wouldn't really be useful on site anyways. To position your pile, you'd always be moving your crane, constantly changing things just to get the pile in the right position. So David, if we wanted to see the effect of a bigger crane, are there any options that you'd want us to check out for something with a little more capacity?
Let's just show a different brand. You want to go with the Senebogen?
All right, so let's we'll go back to our crane tab here, go down through the options. So we'll choose a Senebogen. We'll choose a 6130. It's got the 38 ton counterweight and with a generic serial number. So
Dennis,
it's choosing.
how many ton crane is that?
I think it's a 145 ton crane.
Okay.
So again here,
we said no to the 120. Now we're looking at 145. Okay. Just wanted
correct.
to summarize. Okay.
Yep. So basically, it's just asking us here to update the parameters based on the change in crane. So we'll accept those ones. Again, calculating everything, we'll print it out and see where we end up. All right, so with the new crane, you can see we updated the graphic there, still have the 80-foot boom, 50-foot pile, same drill, but the minimum working radius is how close you can be to the crane is pretty close to the same, maybe due to a few changes in the car body of the crane or the spotter. But the maximum working reach went up from like 29 feet up to 39 feet. So that's the effect of the extra capacity of the crane. So again, our minimum radius is controlled by the boom angle of the crane, so we can't boom this up any further. But because we have the extra capacity and more chart for the crane, we're able to reach out further before we start getting into the situation where we're stability limited. So here you can see in this section of the chart, our max range is up to 39 feet, and we're limited by stability. So again, if we're in a marine job or something, or we got to reach out even further, we can take more advantage of these cranes and sort of choose a bigger crane and see where we end up. Any suggestions, David, on a different crane you want to investigate?
Let's do another one. Cabelco. Let's go all the way up to 200 tons. So the CK, I think it's, what is it? CK 2000.
All right, let's see what we got here. So Cabelco crane model CK 2000. So it's a series 2 that we've got already loaded in here, and serial number generic. So again, if we have specific serial numbers, we can include those. If we have, otherwise we just typically use a generic chart from the product manual. So again, we'll update the parameters based on the new crane. We'll make sure we're comparing apples to apples. So we'll choose an 80-foot crane boom. And we'll rerun the stability analysis to see where we end up. All right, so again, new crane. You can see the numbers didn't really change that much. So here with the 200-ton crane, our minimum working radius is still around 30 feet. And our max radius only went up from 39 to 41 foot. But again, here, if you start looking at the numbers, our minimum reach is now controlled by this retracted length of the spotter, and our maximum reach is controlled by the maximum extended length of the spotter. So basically with that spotter, we're reaching out as far as we can with the spotter, but at that position, we're only at 70% of the crane chart. So really, to take full advantage of the extra capacity of the Cabelco crane, we've got to start changing other parameters in the system. So there we can go back to the spotter tab, and this HHH 12 spotter is one of our shorter ones. We'll switch that to a 3-stage spotter, BK 19 or 1941. So that has a minimum reach of 19 feet and a maximum reach of 41 feet. So again, made that update. We'll calculate the stability and see what effect it has on our range here. All right, so there you can see after that update, our maximum working range jumped from like 41 feet up to 51 feet. So our minimum working radius increased as well. So with the longer spotter, with the increased travel, we pushed that out a little bit, but we're ending up having a 15-foot working range that we can now move the lead out to. So I guess with this little button, you can sort of see the position of the crane at the max reach and at the min reach. So here that was min reach, and then you can see as you extend the spotter and boom down the crane and adjust your vertical travel line, you can reach all the way out to 51 feet. So here again, we're still limited by stability. So we're reaching out pretty far with a 200-ton crane. We're able to accomplish more piles on the grid, but any other suggestions you want to look at, Dave?
Let me just summarize this. So we have at the 145 ton, we were 40 feet of reach. At the 200 ton, we were 51. Why don't we just go super big and take a look at a 300 ton crane? Your choice.
All right, so let's see what we got in here. I know we've done a lot of systems on Manitowoc 2250s, so let me get in there. So Manitowoc 2250, we'll choose a Series 3. Typically, we like to use the most crane that we can. And then here on the serial number, you can see we've got, for this particular crane, we've already got the list charts for barge work loaded in there. So we have done quite a few jobs with 2250s on the crane. So once we have these load charts installed, it's pretty easy to evaluate what kind of stability we have on using the different barge charts. So for this model, we're assuming we're working from land, so we'll choose the generic chart. Again, updating the parameters based on changing the crane. Because we're reaching out so far, you can see this upper slide is starting to move down the lead. So I'm going to choose a longer boom length here just to, and then rerun the calculations and see where we end up. All right, so here we can see the maximum reach. We were at about 51 feet. So with just going to the bigger crane, we're now at close to 60 feet of reach. With the longer boom, you can see we're, again, close to the top of the lead. But if you look at the limits here between max reach and min reach, we're only at 51% of the capacity of the crane here. So we could reach out a lot farther, but we're limited by the spotter. So again, we're going to go back in there. I'm going to choose the longest spotter we currently manufacture, the BK3 2456. So that extends from 24 feet all the way out to 56 feet. So we updated the spotter. We'll recalculate here. All right, so with that new spotter, you can see we're reaching out even further. So now the max reach is up to 74 foot 6 inches. Our min reach also increased. So to get that amount of stroke on the spotter, obviously the retracted length increases as well as the extended length. So now we're reaching out really far on to get that pile position, but we're only still using 72% of the crane chart. So one thing we can do here is with our custom manufacturing, we're able to create a longer heel extension. So I don't know if this is visible on your screen. You can see a short little section here. That's referred to this heel extension length. So we've been using a 36-inch heel extension. So from the point you pin onto the crane out to the heel of the spotter is 36 inches. If we were to make a custom one quite a bit longer, that would push this out even further. It would increase your max reach. So let's go in there. We'll change the default from 36 inch, 3 foot. We'll push that out to a 15-foot spotter. So that's 180 inches. So we'll got that. Everything else stays the same. We'll recalculate and see where we end up here. So now, yeah, this is showing the increased length. We have 180 inches there, so you can see that changes the length of this position here. So the spotter is starting at that position, and now we're reaching all the way out to 86 foot 5 inches. So again, we're not quite maxed out on capacity. At this max reach, we're still at 90% of chart, which gives a little bit of margin for extra weight or extra reach. Extra reach would require something, again, to be a little bit longer. But again, the whole point of this exercise is to show what affects different crane sizes, different components, and how we're able to quickly evaluate all these different choices to come up with a lead solution that'll meet your needs. So with that, I'll pass it back over to David.
Thanks, Dennis. I'm just going to load the screen back up here. Hopefully everybody can see that. So before this presentation, another colleague of mine, Stefano Gabaldo, the international sales representative, he actually worked out the same sequence that Dennis was working at. He worked through the case study. And what he did is he laid out the working ranges on this slide. So you can see the same end results as Dennis came to. The 145 ton seemed to be the smallest that made sense. The 200-ton crane, you can kind of see, okay, let's follow out the line. So the 145, you could capture these 3 piles. The 200-ton crane, you could capture these 8. And then with the 300-ton crane, you could capture 38. So it just gives you an idea. I mean, there's lots of different cranes that these leads can go on. Again, we could have also sized an H28. We went with the minimum requirements for the job and then picked a crane based on the absolute minimum. It would be 145 ton. But if you want to do all of these piles at once for one location, 300-ton crane. So there's lots of different factors that go into picking a lead. Some that Dennis didn't even show is if there were any batters on this project, our software now allows us to analyze both in and out batters as well. So it's just, I like going through that configurator process with all of our customers because it helps them understand why we pick leads for which sizes. It's not that a typical lead just comes with a typical crane. It's we're sizing leads appropriately to the job that needs to be done. So with that, I will actually just play this video, and then Milan, sorry, I didn't have time to take a look and see the questions as we're going there. If you can just read them out to me, I'll see what I can do about answering them.
Yeah, should be pretty easy. There's so far no one's had anything except for Steve asked, will the presentation be recorded and available online? I replied, this was on the group chat there. Yeah, it will be, but he said where the link will be found. I know previously we sent emails. I'm not sure if we're going to be putting up a link specifically somewhere for anyone to grab it, or we send it out individually.
Yeah, no problem. Because of that request, what I'll do is I will put the link up on LinkedIn. Post it kind of just as a separate post, and there's got to be some questions out there. Maybe we'll open it up to the floor. Maybe if you can select the raise the hand button, we'll see what we can do about answering questions live.
If nobody's got anything, there's I think it was so far it was a very good presentation. You cover a lot of material, you and Dennis both. It was a lot of good information. I think a lot of folks on here are familiar with our VTL systems. I think this gives a good summary for those folks at least. Let's see.
Yeah, I'll take this moment, maybe a couple of questions will sneak in right now, but I'll take this moment to direct you to the chat window. At the beginning of the presentation, I put myself, Milan, Stefano, and Louis' contact cards in there. So if you want to save those for your use later, if you have a project where you're considering vertical travel leads, we'd be more than happy to help you out.
All right, we got a question from Todd. Thank you, Todd. It's what sets you apart from other leads manufacturers?
What sets us apart from the other lead manufacturers is actually what you just saw live. The analysis, the engineering that Dennis just did with the configurator software, the analysis they do outside of the configurator software, finite element analysis, there are SolidWorks models that lead to the finite element analysis. We are a highly engineered product, and our manufacturing is also all done in North America. So that's one of the biggest things.
I guess to add to that too, we're like we have our custom leads, but I guess quite a bit of our jobs take those custom leads and develop them for our standard leads and develop them for custom applications. So you can see all the different slide, vibro applications, drilling applications, hammer applications. So if you just buy leads, then it's sort of be up to you to make it fit your tools. Where with Berminghammer, we've done so many jobs where we're fitting tools to leads or new gates, different applications. So a lot of the custom engineering work really sets us apart.
Yeah, we have very strong relationships as well with all of the crane manufacturers. So that's another one. You might have seen a lot of Bauer ones for our H leads, but we've worked with everybody, as you saw from the list of preloaded crane charts in our configuration.
One of the other things that with Berminghammer as a manufacturer, we've had our construction group has been going on like since 1897, and that's how the VTL was developed from the own construction needs. A lot of our work is generated from external customers, such as most people on here. A lot of it is internal. Our own construction, foundation, piling, drilling requirements, needs are custom manufactured for that, and then we see, all right, can other people use it in other parts of the world? And so we actually have a good, I'll call it a test bed of our own construction group. You know, their needs are front and center for us as well. So there's a lot of direct knowledge from our own group. Kendall was asking, apologies if covered this, run through what contractor can expect as a first-time user of a VTL system, either driving piles or CFA, such as setup, teardown, testing, maneuvering on site, etc.
Okay. So traditionally pre-pandemic time, what we do is we'd send a service technician and we'd have them come out and guide you through the process. It's relatively simple. The first thing you do would be to lay out the leads, attach them all together. Depending on the length of the lead, there's some leads that we attach extreme length with a hinge, but if it's just a simple set around 130 feet, probably more than likely you won't be using a hinge. Depends on the crane, but we'll lay them all out, and then you boom down you run all your wire rope, and then you boom down into the boom tip connector, and then you loft the leads without the spotter on. You put the spotter on after the leads are up in the air, and you from there you put your tooling on after your leads are vertical. In terms of what we would do, our technician would guide you through that process. We have a technician with us, his name's Ryan Chevalier, who's probably done over 100 rig ups now. So since the pandemic, what we've been doing is virtual preparations. So about a week or two prior to the actual desired rig up, we'd have a meeting with the people that would actually be doing it on site. And we'd go through that process in a meeting such as this. I'm using our mouse now to illustrate on the screen, and we do the same thing using the configurations, and we'd go through the manual step by step with the lofting procedure with the people that are actually going to do it. And all of us are on call. Some customers have actually live streamed their loft as we've watched. Does that answer your question?
I think you covered everything pretty well. We do a lot of work. We spend a lot of time with each customer. That's the bottom line on their specific needs, as much as they need from us in the development or pre-development. So, yeah, Kendall. Yes, sir. Thanks. All right.
Good.
Excellent. There you go. I can stop talking now.
Anything else, Milan? We're coming up close to the hour, so it might make sense to wrap up.
Yep, I think so too.
All right. Well, I want to say thank you to everybody for watching. Hopefully it was informative. Hopefully you learned something. Even if your takeaway is that, wow, you can put a lot of other things other than diesel hammers on vertical travel leads. That's a good takeaway. I hope it would be that there's a lot of engineering analysis that goes into putting these leads together, and we have a group of professionals that are very good at what they do. Thank you. Talk to you later.
Absolutely. Thank you, everyone.